Maestro now includes some prototype scripts for Rhino. These scripts are intended to help with using Rhino to generate Maestro models and with transferring that geometry data back into Maestro. This video will provide an overview of the script to export beams from Rhino to Maestro, followed by some tips for using it. To execute the script in Rhino, go under the Tools menu and select Rhino Script, Load. If this is the first time using it, you'll need to hit the Add button and then navigate to Maestro Data, Models and Samples, Rhino Scripts, and select the Export Maestro Beams file. Once it's been added to this dialog, you can select it and hit the Load button to execute. As you can see, there are currently 5 options for generating the exported beams. We'll be discussing the first 4, since the 5th one is actually just a placeholder at this time. In each one of these, when we refer to the polylines, that represents the toe trace of the beams we're trying to create. We'll go through the first 4 with a quick description, then we'll do some simple examples, and then finally follow up with some examples on a notional ship for a more real-world demonstration. In the first option, Polyline indirection, this will take any number of polylines in 3D space and a user-specified direction and generate the beams. In the second option, Polyline on mesh, it'll take a series of polylines residing on a mesh and use the mesh normal to determine the direction of the web for each segment of the beam. In the third and fourth options, which are very similar, it takes a selected mesh as well as a specified direction and angular tolerance and tries to extract the beam traces from the mesh. In option 3, polylines, it stops there, and the polylines are available for the user to edit and then go back and export using option 2, Polyline on mesh. In the fourth option, beams, it continues on and actually exports all of those extracted polylines as beams and then presents the user with the option to either save those polylines for additional editing and re-export or to just delete them altogether. Finally, the last option, the placeholder, if that were to be executed, the user will simply get a notice saying that it doesn't exist yet. To illustrate the first option, polyline indirection, we'll use 2 random polylines, one of which is planar and the other is non-planar. These can either be pre-selected before running the script, and if they're not, the user will be prompted. Since we've already run a script in this session of Rhino, we can right-click in the command history window and select the load command from there. When we go to export with polyline indirection, we're first prompted to select our polylines. Once we hit enter, we're given the dialog box to enter the direction for the beams. There's a quick list of the positive and negative directions of the 3 primary axes, or the user can manually type in whatever vector they want. For our first export, we'll export in the negative z direction, which in Rhino is the vertical direction. This would be as if we were doing stiffeners under the deck. So we'll call this demo 1 down and export. And while these are still selected, we'll run the script again. You can see we're no longer prompted to select the polylines and go straight to the dialog for the direction. We can put in 0, 1, 1 for our new direction. And we'll call this file demo 2 0, 1, 1. We switch into Maestro and import those neutral files. When we bring in the first one, which was extruded straight down, you can see in plan view that they are exactly vertical. And when we import the second one, which was extruded in the 0, 1, 1 direction, we can see how they line up relative to the first one. Now, each of these beams has a nominal height of 5 inches, which is what the script uses during export, so that the beams will be visible in the model, regardless of which units you're using. Currently, The script will only use units that are available in Maestro, which is inches, feet, centimeters, millimeters, and meters. To illustrate the second option, polyline and mesh, we've created two meshes, one a small sphere and the other a warped plane. The plane twists as it moves forward in the x direction, similar to how the shell plating might twist upward as it approaches the bow. For our curves, we created 3 polylines, one on the sphere and 2 on the warped plane. And if we turn the points on, we can see that the points defining the polylines correspond to the mesh vertices. If we select our curves and then execute the script, since the curves are pre-selected, it won't ask us to select them here, and we'll go straight to prompting us for the reference meshes. Since we have polylines on both meshes, we'll select both for our reference meshes. And then we'll save them poly and normal. We'll also export the actual meshes, so we'll have the reference surfaces in Maestro to look at. Before we switch to Maestro, we'll check the directions. We can see that the sphere has an outward normal and that the warped plane is pointing in the upward direction. When we come into Maestro and import the polygon mesh surface, we'll toggle the points on and off, and now we have our reference meshes. And then if we import our beams, you can see that they show up on the outside of the sphere and the upper surface of the warped mesh. As we zoom in, we can see that the normals of the beam along the length of the mesh match the normals of the mesh. To illustrate the third option, mesh indirection to create polylines, we'll reuse the warped rectangular mesh from the previous example. But as you can see, we've modified it to split some of the quads, to add some additional edges in here, and some triangular elements. When we execute the script, the first thing it's going to ask for is to select one or more meshes from which we'll extract polylines. Once they're selected, it then asks for the direction, which is defined by 2 points. So if we set the base point, we can set for this example, an additional point right along the x-axis. Then it'll ask for an angular tolerance. The user can put any value they want in here between 0 and 80 degrees, but there's also a pre-populated list of some common angles to use. So if we use 20 degrees for this first attempt, you'll see we get most of the edges that we wanted to extract, but it's not quite large, or the angle wasn't quite large enough to allow us to get the other end of the mesh. If we delete these, our choices are basically to either increase the angular tolerance from the existing reference direction, or select a reference direction that's closer to the average of the polylines we're looking to extract. So if we rerun with a larger angular tolerance, say 30 degrees, we'll get all of the polylines that we were expecting. We delete those and similarly try using a direction that's closer to the average of the polylines. We can actually bump that value down to 15 degrees and still get all of the polylines we were expecting. It's really up to the user which way they want to go, but most likely there's going to be some editing required of the polylines before they're exported as beams. In this case, if this was, say, side shell plating and we were extracting the longitudinal stiffeners, we most likely would not want these curves at the edges, since there would be a deck below and above this section, and these additional pieces in here would need to be removed. Now, there's no control over how exactly the script joins the curves, so you have to check each one, and in this particular case, for editing this curve, the user would have to either explode the polyline and deselect the segments they didn't want, or they could turn on the mesh points and delete them really up to the user how they want to go about the editing. Now if we select all the curves, we can join them if we want, just to clean things up a little bit. And if there's any additional editing, we can go ahead and make any modifications that are required before exporting. And now we could select these curves and use option 2, polylines on mesh, to actually export these beams. The example for the fourth option, mesh indirection to create beams, is essentially the same as the third, except the beams are exported automatically and the editing is done in Maestro. If we go ahead and rerun the script with the same settings as option 3, you'll see we get the same polylines created, and then we're presented with a dialog as to whether we want to keep these polylines for later editing or simply delete them. We'll go ahead and delete them, and then we're asked for the file name where we want to write out the beams. We'll call it option 4. And we'll also export the mesh so we have it as a reference. When we come into Maestro, we can import our polygon mesh, and then import our beams. And you can see all of the beam traces have come in, and we can clean them up in the deletions dialog. If we select one beam element from that edge and then add by seed, it'll take the whole beam trace. And then we'll simply do that to the other side. But you can see it's selected a few unexpected beam elements in here. That's likely due to duplicate FE tag. So we can not delete those and refresh. And we'll go ahead and renumber FE tags. See if that fixes the problem. It's always a good idea to renumber the FE tags when you import a polygon mesh file or the Maestro neutral file for the beams. And now when we do the exact same operation, you can see we only get the beam traces that we were interested in. And then we can go ahead and add those remaining individual beam elements to delete. As I mentioned earlier, these scripts are prototypes and were created to test desired functionality, required features, and of course, for debugging. There are a couple things that the user should be aware of when using the export beam script, and both of them have to do with using a reference mesh for setting the beam orientation. The first is that all the points on the polylines must correspond to vertices in the mesh, and the second is that when using multiple reference meshes, if a polyline happens to lie on two different meshes, there's no way to control which mesh will be selected for setting the normal. To illustrate the first point about the polylines needing to lie on the mesh vertices, let's look at this flat rectangular mesh. We've already extracted the polylines in one direction, and if we turn the points on, we can see that they all lie exactly on the mesh vertices. Now let's say after the polylines have been extracted, we need to edit the mesh, and in this case, we'll take a couple of the mesh points and just slide them along the polylines so that those mesh rows are still coincident with the polylines, but the nodes no longer line up. And in another section, let's insert an additional node to tie into, say, some adjacent structure. Now, similarly, let's say the polylines were not necessarily extracted from the mesh, but rather they were created manually by clicking on the vertices. And let's say we missed one of the vertices by a small amount. And also in an adjacent row, let's say we missed a vertex altogether and delete that node. Now, if we write out these beams using the script, and we'll call these this file beams, and then we'll also write out the mesh. Now, before we look at this in Maestro, let's take a note of the direction of the beams. So they all run left to right. In Maestro, if we import our mesh for reference, and then import our beams, we can see that where the nodes didn't line up, we're missing some beam segments. Now, since the beams ran from left to right, it's the first node on each segment that's used to compute the normal. So when it reached this segment, it had no node on the mesh to use as a reference for the normal, so it didn't write it out. Similarly, when we missed that one node from editing the polyline, where it was slightly off, the first segment did get written because the first node had a corresponding mesh vertex, but the second node was skipped, or the second segment was skipped. And the segments where we've inserted an additional mesh vertex, or in the case where we missed one of the mesh vertices when drawing the polyline, you can see because it had a mesh vertex at the beginning, it was able to compute the normal and create the beam. But the user should be aware that when it fails to write a beam segment, there's currently no warnings given. To illustrate the second issue of having a polyline with more than one reference mesh, we'll use this mock-up of a longitudinal bulkhead and a transverse bulkhead. The polylines have already been extracted for a vertically stiffened bulkhead. And if we run the export script with both meshes for reference, and we'll call this beams 2 refs. And then we'll try the same thing using just the one reference mesh. And for reference, we'll also write out the actual meshes. And now we'll read the mesh and beams into Maestro. And we'll start with the beams that use 2 reference meshes. And as we can see, that beam in the corner selected the wrong mesh for computing the normal. And now we'll read in the beams that only had one mesh as an option. And then if we turn off visibility on that first set, we can see that the beam now selected the right orientation. If working with groups of polylines and meshes, an easy way to avoid this situation is to just operate on the transverse bulkheads, longitudinal bulkheads, and decks separately. Now that we've reviewed all the options for the script, let's move on to a more practical example using a sample hull form. Here we have a mock-up of the second deck of a vessel approximately 160 meters in length. We've added transverse subdivision bulkheads every 20 meters along the length of the hull, as well as some additional longitudinal and transverse structural bulkheads in the after portion. For reference, the mesh size here is a ½ meter in the longitudinal direction and 0.6 meters in both the transverse and vertical directions. And we'll use a frame spacing of 2 meters for this demonstration. To start, we'll extract the beam traces for the deck surface first, and then we'll move on to the side shell and then the internal bulkheads. So first we'll load the script and extract the longitudinal stiffeners. And for this we'll use a 5-degree tolerance because all of our mesh lines are very straight. When the script is done, all the mesh lines are highlighted, and we can see we have some cleanup work to do here. One, because it selected a curve that is on the side shell, and also if we zoom in, we can see that it missed a few segments at the very end of the stiffeners because they either taper in or taper out to match up with the mesh on the side shell. Now, typically in the bow, this may transition to a transversely framed, and a lot of these stiffeners will likely end at the nearest frame and have intercostals put in up forward of them, as well as like on the side shell here, or near the side shell rather, there may not be enough room to weld, so they'll stop the stiffener a little early and put in intercostals. For now, we'll simply click on some of these curves to see how we should clean them up. This one we can just delete, and if we select all curves to find where we have other issues, we'll see that this one ties into one of the stiffeners that we want to keep, so we'll turn on the points and then just delete the polyline points that we don't want. And this type of cleanup is outside of what we want to demonstrate in the video, so we'll speed some of these operations up. And now we have our longitudinal stiffeners cleaned up. Personally, I like to group these because it makes it a little easier to select and deselect them later on. So we'll reselect that mesh, and now we'll extract the frames. Now, as I mentioned, the frame spacing we're going to use is 2 meters. So the user can either manually select the appropriate curves at 2-meter intervals, or there's another script that I had written which will just save the curves we're interested in. We'll put in one of the reference locations, which in this instance 0 will work fine, and then put in the interval that we want to keep, which is 2 meters. And it'll simply throw out any of the curves that don't lie on those 2-meter intervals. And now we'll create a group for these curves. And now we can select the ones we don't want, but we're selecting additional things in here, the bulkhead meshes. So we'll go ahead and select the rest of these curves and then deselect all of the bulkhead meshes. So now we just have all of the transverse polylines that we're no longer interested in, and we can delete them. And we can see that we have a group for the stiffeners and a group for the frames. Now for the watertight bulkheads, or I'm sorry, the subdivision bulkheads, we're not going to want those frames below them. So what we can do is ungroup and then start deselecting those particular curves. And then regroup. And now we'll do something similar to what we did before. And just grab all of the curves that we're not interested in, deselect the bulkheads, and delete them. And now we're basically done with the beams for our deck. So let's move on to the side shell. Now to extract our longitudinal stringers on the side shell, we need to wrap all the way up around into the bow here. So let's pick an angle that's somewhat, on the average for what we're interested in. So we'll turn off ortho here and use something like that, and a fairly high angular tolerance, say 70 degrees, and we'll see what we get. You can see we got almost all the way around to the bow, and we got everything back to the transom. So we'll just clean up this area in the bow, and we can't control how they were joined, and if we look at them, we can see we got some odd connections. So what we'll do is select all of the curves, and we can deselect the two groups that we had for the deck previously. and now explode them. Deselect the curves that we were never interested in. And just keep those longitudinal stringers. And then rejoin them. And now we can just drag a window around these and delete those extraneous polylines. And to complete these stringers up into the bow, we'll just add the additional polylines that we need. And if we deselect select all curves, deselect the ones on the deck, and then join them, now we have all of our side shell stringers. We'll want to get rid of the ones at the deck and at the main deck. And if we select the curves again, we can see that because we had some shear up in the bow forward, some of these lines start to go along the decked edge. So we'll need to clean those up a little bit by just turning on the points and deleting the polyline points we don't want to keep. And we have a similar issue on that one, but that one runs all the way back to the stern. So it might be easier to explode this one, deselect a segment, rejoin, and then delete those two curves. Now we'll deselect the curves on the hull, and we have all of our side shell stringers, so we'll create a group. Now that function would be the same on the opposite side, but for purposes of this demonstration, we'll just deal with the starboard side. Next, let's create the side shell frames. So we'll select the side shell and run the script again. And we'll use a vertical line for our frame direction and a 40-degree tolerance. See if that gets everything. It seems to have grabbed everything we needed, although we do miss a few things up here in the bow where there's a lot of curvature. Now we know we only need the frames at 0 and 2 meter increments, so we will need to complete this frame, and the next one is already complete there. So we'll explode all of these curves and remove the curves adjacent to the one we want to keep. And then build the polyline to complete that curve. And now we can join them all together. We'll grab some of these extraneous curves up in the bow and delete them. And now we can select all of the curves. We'll remove the curves from the deck. We can leave the longitudinal stringers on, the side shell stringers selected, because when we run the other script to deselect anything that's not at those X intervals, they'll get thrown out immediately. So we'll use the same script with the 2 meter intervals. And now we can make a group for those, and similar to what we did before, we'll grab all of the extra lines there, although now if we try and deselect all of those bulkheads, we're going to wind up deselecting all of those curves too. So an easier way of doing this would be to select all the curves and then deselect the groups that we had defined. And that's where having them all grouped comes in very handy. So now we have just the remaining curves that we want to delete, and we can get rid of them. And now the curves we currently have are Well, we still need to edit those frames. We do have frames that land on bulkheads, so we'll do the same thing we did with the frames under the deck, and we will ungroup them, remove the ones we don't want, regroup them, and then we can delete those that landed on the bulkheads. So finally, we'll do the transverse and longitudinal bulkheads. We grab a lot of these bulkheads at the same time. We'll do a bunch of the transverse bulkheads here. We'll just work in the aft portion for now, since this is just a demo. And these will be vertically stiffened bulkheads. And once the beams are extracted, we'll then remove those polylines where we wouldn't have stiffeners in the model, such as corners and bulkhead intersections. Now, if we miss any, we can always delete them in Maestro. So let's go ahead and group these, and then we'll remove all the meshes and polyline group. We'll go ahead and delete those extras. Do something similar for the longitudinal bulkheads. For now, we'll make these vertically stiffened, although we could also extract the longitudinal stiffeners and simply use that other script to keep the X intervals for any vertical frames that we want to keep on these. But for now, we'll just do the same thing that we did on the transverse bulkheads. We'll remove polylines from the corners and intersections, make a group, and then clean up the extra polylines. So now we have all of our beam traces. The nice thing about having the beam traces on the internal bulkheads is that when we select the meshes, and we'll turn off the deck, side shell, and transom. And if we turn on direction, and if we use the polyline and mesh option when exporting the beams, we can use the normal on the mesh to determine which side of the bulkhead those beams are going to be on. So if one of these, if we wanted the bulk or the stiffeners on the forward side of this bulkhead, we simply flip the normal. Which can make it easy to rearrange these things. Using the normal will take a little more time in exporting the mesh or exporting the beams, but it can save a little work later on. And now we'll go ahead and export the beams to Maestro. So we'll start with the longitudinal stiffeners on the deck. And for these, we don't need the normal. We know they're going to go straight down, so we'll use the polyline and direction. I'll put them in the negative Z direction. And we'll call these deck stiffeners. Then we'll load the frames group. And again, use polyline and direction. Put them in the down direction. And call them deck frames. For our side shell stringers, we use the mesh or the polyline on mesh and use the normal of the side shell. And once it's done computing the normals, can write out the file. And similarly, we can do the frames, but rather than use the mesh normal for the frames, we know we want them to come straight in, so we will use the polyline indirection. And we want this in the negative y direction. And we'll call that shell frames. For our transverse bulkhead stiffeners, we'll use the mesh normals again. And we'll select all of the transverse meshes. And once that's done, write out the file, and then do our longitudinal bulkheads, which are essentially the same steps as we did for the transverse bulkheads. And now if we come into Maestro, we can import our polygon mesh file, which has all of our second deck surfaces in it, and then start to import all of our Maestro neutral files for all of our beams. We'll start in the same order that they were written out, although they can be brought in any order. You can see our deck stiffeners and frames are essentially the same height, and that's because they're all currently using the sort of default beam size when they're written out, a sample property that's approximately 5 inches in height. We have our shell stringers and frames, and then finally we will bring in our transverse bulkhead stiffeners and our longitudinal bulkhead stiffeners. Now for assigning properties to all of these, you can see that each group of beams came in its own module, and we can take advantage of that. If we create a new group and add by module, then we can grab one element on, say, the longitudinal bulkheads and grab all of those stiffeners, and then simply right-click, group modify properties, and then change the beams. Right now we only have the sample properties that were brought in with the beams, but ideally this would be pre-populated with all of the stiffener and frame types that would be used in the model, and you could simply switch them over right here. Now the other thing is that because each one has its own unique property, we don't have to keep them in separate modules. We can start merging all of these into our meshes. And now we just have one module for the second deck, which contains all of our elements and all of our beams. And if we view by beam property, we can see they each have their own unique, I guess, quote, sample property. So to assign the properties now, we can simply grab one of those same beam elements for, say, a longitudinal bulkhead stiffener, and then add by property. And we'll get basically the same thing we had before when we added by module. And now we can use the group modify to assign our beam properties for whatever the default would be for each beam type. And that essentially completes our example for how to use the beam export script